So we don't make epoxides just to make epoxides. We make epoxides to open them. So let's look at one set of conditions for opening epoxides. And this is going to be acidic openings. Okay, so let's draw an epoxide. And we're going to look at things like stereochemistry. So it's going to be an epoxide stuck onto a ring. Now, when we open this under acidic conditions, let's open up with water. Let's think of an acid. Sulfuric acid is kind of my go-to acid. Remember, when we mix water and acid, we tend to make H3O+. So when I say we're gonna open something under acidic conditions, that's kind of a clue. Well, the first step is going to be protonation. Protonation with what? Our operating acid, and our operating acid is going to be H3O+, because that's what you get when you mix water and sulfuric acid. So we're going to protonate one of these lone pairs with our H3O+. That's going to give us a protonated epoxide. Protonated epoxides are strong electrophiles. What do strong electrophiles do? They react with weak nucleophiles. And we have a weak nucleophile in here. We have water. So the only question is, where will our water attack? Well, our water will attack at one of the carbons of the epoxide ring. So remember, this oxygen is saying to you it has a positive charge. Please give me electrons. So how are we going to give it electrons? We're going to break a bond to that atom, that oxygen, and give those bonded electrons to the oxygen to form a new lone pair. Well, the oxygen of the water will attack the more highly substituted side and break that CO bond and put those electrons on the oxygen, on the epoxide oxygen. So this water, when it attacks, it comes in from the opposite face. We get the methyl group gets pushed up. This ring on the epoxide oxygen is still up. Note that the stereochemistry at this particular carbon is unchanged. There are no bonds breaking or forming there. So we can just redraw that stereocenter. Now, this would be our product, but it's got a positive charge. We need to take care of that positive charge. We need to deprotonate the oxygen, and to do that, we'll use the best base that we have available. That is water. And what we get is this opening product. Make that more clear. So what have we overall added? Remember, this compound, our starting material, came from this alkene. So what have we in net added? Well, we've added 2 OH groups. We've done an addition reaction. And the overall process is an anti-addition. Although you could argue, once we made the epoxide, making the epoxide is really where the addition occurred. It's where we got rid of the alkene. And this was really a syn addition. But once we open up the epoxide, because the water attacks from the opposite face, in this step, the overall process is an anti-addition. So when you open up an epoxide, you get 2 groups added to your alkene, and they will be trans to one another. So this is opening under acidic conditions. The key thing is, under acidic conditions, your nucleophile, your weak nucleophile, attacks at the more highly substituted carbon of the epoxide. This is not so different from when we made things like bromonium ions or other halonium ions. You know, it looks just like this protonated epoxide. You've got a 3-membered ring with a positive charge, 3-membered ring with a positive charge. It's the same thing. What do we do with this? Well, we said the bromide attacks at the more highly substituted carbon to break open the bromonium ion, and we get the anti-bromide. The anti-dibromide. So really completely analogous processes because the intermediates look the same. 3-membered ring with a positive charge, 3-membered ring with a positive charge.